Good afternoon, ladies and gentlemen, and everyone else. My name is Jake Blanker. My topic is rocket dynamics, Zawolsky and Taylor, and I'm in my C3. And this is Cosmos 2015. So let's hope it's auto-playing, and we'll get to Konstantin Zawolsky. There we go. He's a cool Russian dude. He was born in 1857, died in 1935, and he was an astrophysicist and engineer. And most of his theories, like most of our theories, are based upon the work that he did. He's one of the main reasons why the Soviet-Russian program was successful was because he did a lot of work in the field of astrophysics and aerospace engineering, and most of our theories are based upon his work. Do that again. No? Okay, still have time, apparently. He greatly influenced, oh there we go, sweet. Zawolsky wrote about construction of rockets and all these cool ideas like space stations and how to even use plants to create oxygen for our astronauts if you were to build a space colony. And he did all this awesome stuff, and he was even deaf, and he still managed to do all this stuff because he read a lot. But the thing that we mostly contribute him to is ideal rocket equation, aka Zawolsky rocket equation. That's delta V equals VE ln of MI over MF. I said things really quickly, so we're going to go through this a little slower and point out what each one of these mean. We'll do a fancy term hopefully soon. There we go. dV is the change in velocity of your rocket. Obviously, you're trying to make your rocket go fast. That's how we get places, is rockets move very quickly. VE is the velocity of your fuel that you are shooting out the back of your rocket. Your goal is to shoot fuel rather quickly, thus increases your change in velocity of your rocket. There's also an ln in there. I hope I don't have to explain ln. We're in alter calculus. The initial mass is the mass of the entire unit. It's your rocket and your fuel because it's conservation of momentum, right? So the mass final is just the mass of your rocket itself after the fuel has been burned out. So obviously to get dV faster, you want to have a very high velocity of exhaust, and you want to maximize that ratio of mass initial over mass final, because we want to go very quickly. That's how we get places. Transition. There we go. So yeah, it turns out we could actually, what can we do with this problem? It's cool. It shows us everything about rockets. Well, actually, we can't do quite a lot because it ignores drag, weight, and lift, which are all very important things. Obviously, this is the ideal rocket equation. So it has an ideal situation. So let's analyze each one of those forces. First we have drag. We heard a lot about drag in other presentations. So I'm just going to put the equation up there. There's a bunch of constants, including density, the shape, right? And there's area. There's also the velocity squared. So the faster you go, the higher drag resistance you have. You also have supersonic speeds, which really suck, because overcoming supersonic air resistance is quite a drag. Ha 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 puns. Thank you, David. Yeah, obviously a lot of the energy you use in a rocket is actually just overcoming that drag force because you have to get off Earth. But we can use a lot of these forces to our advantage. For example, if we have fins, right? You have a rocket, you got a fin. Hopefully, when there's a little disturbance in it, it will self-regulate itself by using those fins. Because you can have a stable equilibrium where you have a little disturbance and it goes right back to normal, or it can fly randomly. We can also have a gimbal engine, which is where your engine actually moves and rotates, and then we can adjust the direction of the thrust and adjust our rocket that way. We also can use reaction control systems, or if you played Kerbal, they just call them RCS. They're pretty much little tiny rockets around your rocket, so that you can self-regulate itself. You want them at the center of gravity, or a little bit offset if you want to self-regulate the torque, right? So what this means is the ideal rocket equation does lots of cool stuff, but it's going to get you to the planet, not predict your landing or your takeoff very well. Because when we are out in a vacuum, out orbiting, there's a lot less forces acting upon it, whereas when you're in an atmosphere, you're getting air, you got weight, you got all these other things to deal with. So doesn't that mean it's pretty much useless if we can't predict a lot of stuff? Actually not, because it helps us learn a lot about optimizing our rockets and how to build better ones. For example, multi-stage, chemical optimization, nozzle design. I'm going to go through each one of those because I talk really quickly, so I have just a lot of slides, so I'll talk in a couple of subjects. Multi-staging. That means instead of just, the rockets you fired off yesterday, you have a little engine and then they go, foo. You break it up into stages so that when you burn all the fuel in a section, you get to drop off that section. Then you have less mass. The less mass you have in your rocket, the faster you can propel it because there's less mass to propel, obviously, you know, momentum, mass, velocity. If you lower your mass, you get a higher velocity. So the fuel tank is actually dead weight, and we can shed it off. And you can see that diagram of the multi-stage rocket is actually going farther than the other one. We can also optimize the VE term, not the mass term, by doing chemical stuff that I'm going to talk about in our next slide, or actually nozzle optimization. You know, we learned about this in class. You get supersonic, and you also want to make sure you have the right shape to convert most of your energy into kinetic energy, not heat. I'm not going to go into that because the lovely Albert back there, let's wave at Albert. Hi, Albert. That's his subject.
Hi, Albert.
Good luck, Albert. I believe in you. So yeah, this is how you would optimize the VE term, and hopefully I can talk about fuels when it transitions. There we go. Liquid propellant, solid propellant, two types of propellant. Liquid is liquid oxygen and some hydrogen, kerosene, whatever, right? You mix them together, you burn them, and it's very efficient. It's throttleable because we can adjust the rates at which we are adding these two propellants. Oh, tuned in, cool. The disadvantages of liquid propellant is it's really complicated, much more complicated than solid propellant, and because of that, it's really expensive. It's hard to deal with, it's hard to transport, it's hard to build, and that means that it's obviously just more costly to deal with. Solid propellant, on the other hand, is a solid oxidizer and some just highly reactive chemical that we grind up, put together, right? Think about rockets yesterday. They're just a little thing. You light them on fire, they go. They're not throttleable. You don't have any control of them. They just kind of go once you build them. They're simple, they're cheap, but they're less efficient, and they're not throttleable. You use them on the first stage usually to overcome lift, or overcome drag, obviously. So we learned about this equation. It was fun. We learned how to optimize delta V. But where did it come from? There's a very complicated derivation. It's not actually that complicated, but there's some calculus. And hopefully it's going to transition, and then we get to see it and stuff. There we go. Cool. How do we get this equation? You can just focus on this. I have to do this. I feel like it's my job, but you're not going to be able to pay attention to them very quickly. You turn mass acceleration into dv dt. You turn that into momentum. Once you have momentum, you turn it into differences. That's what we do all the time in this class. We turn dv dt into differences. We can solve for these differences. We can then plug it all in, and since sum of the forces equals 0, we can set this equal to, because we know all this stuff. That's our original momentum, that's our final momentum. We can set them equal, and we get dm over m equals dv over ve. When we integrate that, it's like an exponential equation, or a logarithmic if you want to work your shop it a bit. So when we try and solve for delta v, we actually end up with an ln term in there, that's why. And we integrated from the initial velocity to the final one, which is why we have dv. This is my mathematician. He's Brooke Taylor. He was a cool British dude. Lived 1685 to 1731. Taylor series, you guys. We learned him in calculus. He did a lot of other stuff like finite difference work and oscillations and a bunch of other stuff, but I'm going to focus on the Taylor series. We all know what they are. You have some kind of curve, and you approximate it using linear, and then quadratic, cubic, quartic, quintic, ad infinitum, which is etc., but fancier. This is the equation, right? You have your f prime, x, f double prime, over 2 factorials, something like that. So basically, the closer you are to your origin, the less terms you have to use. But if you use a lot of terms, you can go very far. But we're going to go into an example of how we can use Taylor series to our advantage using rocket dynamics and Wilson's equation and stuff. There we go. Newton's cannon. We did this in class. Problem 1.1, they give you all the initial conditions, and you kind of got to predict your orbit. Hopefully you do orbit, not just crash into the planet. But they only give us the initial condition. If only there were some way we could find a very close point through an approximation. Taylor series, look at that, that's convenient, like I planned it or something. That's our Taylor series equation. So we're going to solve for x of dt, right? Which gives us, x of 0, x prime of 0, x double prime of 0. But we all know that stuff. We can plug things in for that and replace them. That's u, which is the x component of velocity, and that's u prime, which we solved equaling to, angular momentum, so like that, times your x point, and we can replace it with this. Mu is the gravitational constants that we have because we're orbiting Earth. And because of that, we can plug all this in and get x dt equals x naught plus u naught times dt times this whole constancy business times dt squared. Now that we have that, we need to get the generalization. Once again, I'm going to talk very quickly, so all you need to focus on is this, right? We do this for all of our programming. We have u of I, we have u of I plus 1. We're trying to solve for the next one. So we have u of I and u of I minus 1. We're trying to get I plus 1. We do that by taking dUdt equals changes, we turn that into the differences of velocity, and then to the differences of position, and eventually you get three whole terms because you have, you have 2 points, you're trying to get the third, we can set these equal to each other, and then eventually you get this very complicated looking equation, which will get us the third point, but if we have 3 points, it'll get us the fourth point, get us the fifth point, get us the sixth point. But using computers, this is the code that we wrote in our lab. It was very complicated. Like this whole part is just kind of setting conditions that we already know. This is the main business where if we solve that, this is our generalization, right, that we just had on the page. So if you do this just like millions, billions of times, you'll get a pretty little circle, or an ellipse, parabola, hyperbole, whatever. And depending upon your initial conditions, right? So the point is that once we have the Taylor series to get the second point, we can get the third point, fourth point, fifth point by using a ton of computational power and stuff like that. And this kind of combines Cebulski, rocket dynamics, and Taylor into one nice little problem with computers. Cool. Conclusion. Taylor series. It's really, really helpful when we want a point really close. I don't know why I went back. Oh well, yeah. Taylor series is really helpful for when we want a very close point approximation, right? Because if it's close enough and our dt is small enough, we can get a very accurate approximation, even if we don't have crazy, like, f and like lots of derivatives. We only need 2 or 3. And Cebulski's equation is awesome for estimating rockets and generalizing about rockets. But while it's not very helpful, we have based most of our rocket knowledge on that equation. Thank you for paying attention.